Okay, so I want to do another example of the mean value theorem. This one's a little bit trickier. Okay, and so we've got the function 3x to the 2/3 times x minus 4. And we're asked, does the mean value theorem apply on the interval -2 to 2? How about the interval 1 to 4? All right, so remember, for the mean value theorem to apply, our function needs to be continuous and differentiable on that interval. So let's check both of these things. So let's start with -2 to 2. Okay, so on -2 to 2, let's think about whether or not our function is continuous. Well, this function, 3x to the 2/3 times x minus 4, x to the 2/3 is a well-defined cube root function. The cube root function is continuous everywhere. X minus 4 is continuous everywhere. When I multiply those together, I get a function that's continuous everywhere. So this function, 3x to the 2/3 times x minus 4, is continuous everywhere. That means it's going to be continuous on our -2 to 2. Okay. How about differentiable? Well, to determine whether or not something's differentiable, probably the easiest way is to take the derivative. So let's find our derivative, so f prime of x. Notice that this is a product rule problem. I have one function, 3x to the 2/3, times another function, x minus 4. So I'm going to need to use product rule to find that derivative. 3x to the 2/3. Derivative of that will be 3 times 2/3 x to the -1/3 times my second function, x minus 4, plus my first function, 3x to the 2/3, times the derivative of my second function. The derivative of x minus 4 is 1. So f prime times g plus f g prime. Okay, well, I'm going to do a little bit of simplification since we're going to be using this. 3 times 2/3 just gives me 2, x to the -1/3 times x minus 4 plus 3x to the 2/3. All right, since we're going to need this derivative later, let's go ahead and continue to simplify this. So this is where one of those weird factoring techniques comes about. So notice that both of these terms have an x raised to some power, and that power is some version of 1/3. So I'm going to pull x to the -1/3 out. Now that's not too weird. Think about when we're factoring, we generally pull out the smallest power. -1/3 is certainly smaller than 2/3. That leaves me with, in this first term, 2 times x minus 4, plus, in this next term, I'll have 3x, and the trick is to figure out what the power is. Now remember, we're really dividing x to the 2/3 by x to the -1/3. When we divide like bases, we subtract powers. So this would be 2/3 minus -1/3. Well, that's 2/3 plus 1/3, which would be 3/3. But x to the 3/3 is just 1. Okay. Now notice if you want to check that, we check that by multiplication. When I multiply x to the -1/3 times x to the 1, that becomes x to the -1/3 plus 1. But -1/3 plus 1 gets us back to that 2/3 power. Okay. So continuing with our simplification, I'm going to simplify inside my parentheses here. So that'll be 2x minus 8 plus 3x, which leaves me with, inside the parentheses, 2x plus 3x is 5x minus 8 all over. I'm going to rewrite x to the -1/3, moving that 1/3 to the bottom. So that would be x to the 1/3, which I can write cube root of x. Okay, so there's our simplified derivative. So the derivative of this simplifies down to that. Okay, so now let's think about differentiability. Now thinking graphically, a function is not differentiable anywhere the function is not defined, but we know that the function is continuous, which means it's defined everywhere. Anywhere where we get points, sharp corners or cusps, or anywhere that we have a vertical tangent line. Now to look for those things in our derivative equation, we're going to look for places where our derivative is undefined. In particular, our derivative is going to be undefined when our denominator equals 0, and our denominator equals 0 when x is 0. So when x is 0, our derivative is undefined, meaning f of x is not differentiable at x equals 0. Okay. Well, unfortunately, x equals 0 is firmly inside this interval. So 0 is between -2 and 2. So MVT does not apply. Nope. F of x is not differentiable at x equals 0. Okay. So we're not differentiable when x is 0. Now, one nice way to check that is to just look at a graph. So let's real quick pull up a graph of this function. So I'm going to share my screen with you. Okay. So here's on Desmos, I have graphed. Oops, I've got to graph a bunch of things, so ignore that. But I have a graph of the function f of x equals f of x equals 3 times x to the 2/3 x minus 4. Notice that this function, as I zoom out, looks nice and well defined, so it's nice and continuous. However, we look at 0 and there certainly is a sharp cusp there. So we can see from the graph also that our function is not differentiable at 0. Since 0 falls in that interval, that means mean value theorem does not apply on -2 to 2. Okay, so now let's consider the other set of points we have there. Okay, so the other set of points that we have there, 1, 4. So let's look at 1, 4. I'm going to erase everything down here except for our derivative, because we'll still need that. Okay. Okay, well, since our function, 3x to the 2/3 x minus 4, is still continuous everywhere, it's going to be continuous on that interval 1, 4. And thinking about differentiability, remember that the only place our derivative wasn't defined was x equals 0. Since 0 is outside of that interval, 0 is to the left of 1, we are differentiable on 1, 4. So MVT does apply. Our function is continuous and differentiable on 1, 4 on that interval. And if you think back to that graph that we looked at, the function, well, maybe I'll just pull it back up. So pulling back up that graph, from 1 to 4, that function is nice and continuous and smooth. All right, now notice that in this particular case, we weren't actually asked to find the c defined by the function, or defined by the mean value theorem, but let's go ahead and do that. I'm going to warn you right now, this is going to be algebraically a little bit tricky. So tricky, in fact, that we're actually going to use an online kind of solving system to help us at some point. Okay, so we know that MVT applies on 1, 4, so we're going to limit our case to 1, 4, and we're going to try and find the point guaranteed to exist by the mean value theorem. So let's find the c given by the mean value theorem on that interval 1, 4. Now remember what the mean value theorem says. It says if we meet the conditions, which we did, there exists a c such that the derivative at c is going to equal the slope of the line between the endpoints. Okay, so we need to find f of 1. F of 1 looks like 3 times 1 to the 2/3 times 1 minus 4. 1 to the 2/3 is 1 times 3 is 3. 1 minus 4 is -3. 3 times -3 is -9. So our first point is 1, -9. Plugging in our second endpoint, 4, we'll have 3 times 4 to the 2/3 times 4 minus 4. Now 4 to the 2/3 is not a very nice number, They don't really care because 4 minus 4 is 0, and 0 times anything, except possibly infinity, is 0. So our second point is 4, 0. Now remember what this half of our mean value theorem says. It says we want the slope of the line between our endpoints. We now know our endpoints, 1, -9, and 4, 0. So let's calculate the slope between them. So 0 minus 9 over 4 minus 1. 0 minus a -9 is a positive 9. 4 minus 1 is 3. So our slope is 3. Okay. Now over here, on the other side of this mean value theorem equation, we're saying the derivative at some value has to equal 3. Well, luckily we already calculated and simplified our derivative. So really what we have on this side of the equation is we have that 5x minus 8 over cube root of x equals 3. So this is now the equation that we are trying to solve in order to find the point guaranteed to exist by the mean value theorem. Now this is where it gets a little algebraically messy, okay? But that's okay. Let's give this a shot. So the first thing we're going to do to solve this algebraically is we would multiply both sides by the cube root of x. That cancels the cube root of x over on this side of our equation and leaves us just with 5x minus 8 equals 3 times the cube root of x. Now we're trying to solve this for x, so I need to untrap that x. So I'm actually going to cube both sides here. Now cubing the right-hand side is not so bad. I can cube 3. 3 cubed is 27. The cube root of x cubed just leaves me x. Unfortunately, on the other side, I get this. Now at this point, the only thing that I can do is I need to actually expand that all the way out. So I need to expand that 5x minus 8 cubed. Okay. Now I'm going to go ahead and have my calculator do that for me. So it's going to expand this 5x minus 8 cubed by doing 5x minus 8 times 5x minus 8 times 5x minus 8. I would expect you guys to go ahead and use something like that as well. All right. So when I expand this, I end up with 125 x cubed minus 600 x squared plus 960 x minus 512 equals 27 x. Whew. Now this is quite the beast to solve. Okay. Technically, we do have a cube root formula, or a cubic formula, kind of like our quadratic formula. However, no one uses it. I don't use it. I don't remember what it is. So at this point, I would probably take this big old polynomial, and I'd probably write it like this. 125x cubed minus 600x squared plus 960x. I'm going to move my 27x over. Minus 27x minus 512 equals 0. And I would go ahead and put that into some kind of solver. So I'd use my calculator to find the zeros. I would use Simulab to find the zeros. Okay. In this case, since I have Desmos pulled up, I'm going to go ahead and pull that back up and show, all right, here on Desmos, here is that equation. And I'm going to go ahead and turn that on and turn our other equation off. So there's where that crosses 0 at 2.404. So this is saying x equals we'll just round that to 2.4 is our solution. In other words, this, if I plug this into my derivative, I should get 3, or approximately 3, since we've been doing a little bit of rounding. Okay. All right. So the last thing that I want to do is I want to go ahead and look at a graph of this real quick. So I'm going to pause for just a minute. Okay, so let's look at what we've got here. Again, in green is our original function, 3x to the 2/3 times x minus 4. The endpoints of our function, okay, 4, 0, and 1, -9, just like we calculated. And then here's that little point that we found, that 2.4. So the blue line is the line between our endpoints, and we can sure see that that has slope of 3, 1, 2, 3 over 1. And then our orange line is the tangent line at 2.4. That's that point that we calculated. And that sure looks to have slope of 3, 1, 2, 3 over 1. And those two lines, the orange line and the blue line, are parallel, just like we're told they should be in the mean value.